Welcome to our group project, ECG 565, Road Safety Audit, prepared for IRTS Dr. Rosmawati Mamat. Here is our group members. The first test conducted is outflow meter test. Procedure. 1. Prepare the complete apparatus and find a suitable place to conduct the experiment. 2. Before the test begins, make sure there is no vehicle that obstructs the experiment. 3. Next, set up the outflow meter apparatus and fit it with the stabilizer board, then place it on a pavement surface. 4. Then fill up the outflow meter tube with water for 300 milliliters and make sure that the valve at the bottom part is closed. 5. Open the valve and press the stopwatch at the same time the valve is opened. 6. Record the time taken as the water flowing out from the outflow meter tube according to the level of water that has been set. Steps 1 to 6 are repeated for the smooth, medium, and rough surface. The data collected are tabulated. This slide presents the experimental results of the outflow test conducted on 3 different surface types, which is smooth, medium, and rough, using a constant surface volume of 300,000 millimeters cubed. The smooth surface recorded the lowest flow rate at approximately 156,116.87 millimeters cubed per second, indicating slower water discharge and higher water retention on the surface. In contrast, the rough surface achieved the highest flow rate of about 53,285.97 millimeters cubed per second, demonstrating the most efficient drainage performance among the 3 surfaces. The medium surface showed a flow rate of approximately 43,795.62 millimeters cubed per second, which is lower than the rough surface, but still significantly higher than the smooth surface. Overall, the results indicate that increasing surface texture improves drainage efficiency, with medium and rough surfaces allowing faster water evacuation compared to smooth surfaces. This graph visually compares the rate of flow for smooth, medium, and rough surfaces. From the graph, it is clearly observed that the smooth surfaces has the lowest bar, confirming its poor drainage capability due to longer water flow time. The rough surface shows the highest bar, reflecting the highest flow rate and the most effective drainage performance. The medium surfaces appears slightly lower than the rough surface, but remains substantially higher than the smooth surface, indicating good drainage efficiency. This graphical representation reinforces the experimental findings that surface texture plays a crucial role in improving water discharge and reducing surface water accumulation. Next is the sand patch test. This sand patch test also conduct in dry and wet condition with 3 different surface, which is smooth, medium, and rough. The apparatus needed in sand patch test is sand. Next is ruler, cylinder, brush, spreading tool, and lastly, cone. Firstly, clean the pavement surface before testing using brush. Next, measure the volume for 20 milliliters of sand before spreading. Then, carefully pour the measured sand onto the test surface. Next, spread the sand in a circular motion. Lastly, measure the diameter of the sand circle in at least 2 perpendicular directions and record it. The results show for the result for sand patch test, where at the end we should calculate the value for mean texture depth to get the MTD by using formula 4V over pi d squared. The last test conducted is skid resistance test. Step 1. Equipment setup. The British Pendulum Tester, BPT, is placed on the test surface. Adjust the spirit level bubble until it is perfectly horizontal and level before use. Step 2. Zero calibration. The pendulum is released without touching the surface. The pointer should read 0. Release the pendulum and allow the slider to pass over the surface. Record the skid resistance value, SRV. Repeat the test at least 3 times. This test was also conducted in wet and dry condition in all 3 surfaces: smooth, medium, rough. As for the results, when compared with the JKR standard JKR/SPJ/1988, the smooth surface meets the requirement in dry conditions but does not comply under wet conditions. The medium surface satisfies both dry and wet JKR limits. Meanwhile, the rough surface exceeds JKR requirements in both conditions, showing the best overall performance. This confirms that increased surface roughness significantly improves compliance with JKR standards, especially in wet conditions. Moving to our comparative analysis, we evaluated the 3 surface types against established standards and their practical impact on road safety. First, against local JKR requirements, smooth surfaces only meet the absolute minimum drainage criteria and are considered marginal. This means they barely pass but are not recommended for safety. Medium textured surfaces are fully compliant with all recommended performance standards. Rough surfaces don't just meet the standards, they exceed the recommended drainage performance. When benchmarked against international AAHTO guidelines, smooth surfaces are at the lower bound of acceptability, which aligns with their high-risk profile. Medium textures fall securely within the good practice range. Rough surfaces exceed the typical international benchmark, indicating superior engineering performance. Now for the most critical part: drainage effect on safety. Smooth surfaces are only marginally acceptable. The slow drainage we measured directly leads to water film formation. Medium surfaces are fully compliant, offering reliable water dispersal to maintain tire contact. Rough surfaces are highly compliant, providing the fastest water removal and the lowest risk of hydroplaning. Finally, let's talk about perceived road efficiency, what this means for drivers on Malaysian roads. A smooth surface translates to an increased skidding potential during our frequent rainfall, a clear safety deficit. A medium textured surface provides a significantly reduced hydroplaning risk, ensuring predictable vehicle handling in wet conditions. This balance makes it highly efficient for most of our highways and urban roads. A rough surface offers the highest possible skid resistance, which is excellent for critical locations like sharp curves, approaches to toll plazas, or steep gradients where maximum grip is needed. In summary, while smooth pavements may seem adequate on paper, they represent a compromise on safety. For overall efficiency and compliance with both JKR and international standards on Malaysia's wet roads, medium textured surfaces provide the optimal balance, and rough surfaces offer maximum safety where it is most critically needed. Moving on to discussion. For the outflow meter test, measuring drainage capacity, the results directly correlate with texture. Smooth surfaces failed dramatically, with the slowest drainage time of over 19 seconds, confirming very poor water clearance and a high risk of hyperplaning. In contrast, both medium and rough surfaces drained efficiently. The rough surface was the standout for drainage, moving water at a rate over 3 times faster than the smooth surface, thanks to its high roughness and interconnected void network. For the sand patch test, measuring texture depth, the test revealed how texture affects water drainage and tire contact. Smooth surfaces can misleadingly show a larger spread of sand, but this is because the sand rolls across the flat surface. In reality, their lack of deep voids allows water to pool. Rough surfaces confine the sand to a smaller area, confirming they have abundant, deep voids crucial for channeling water away. For the skid resistance test, smooth surfaces are dangerously slippery when wet, showing a severe drop in friction because water forms a film with nowhere to go. Medium textured surfaces provided the most balanced and reliable performance, maintaining good grip in both dry and wet conditions, making them ideal for most urban and highway applications. Rough surfaces offered the highest overall skid resistance. Interestingly, they sometimes performed slightly better when damp, as the thin water layer reduces rubber vibration and improves mechanical grip.